All right, today in The Explainer, we're jumping into something we literally use every single day, maybe without even thinking about it. We're talking about whole numbers. So yeah, let's break it all down. So, to get us started, let's kick things off with a little question. What do 3 apples, 100 steps, and hey, 0 errors, what do all those things have in common? I mean, they seem pretty different, right? You've got fruit, distance, even mistakes. So what's the one thing that connects them all?
You guessed it, they are all counted with whole numbers. Think about it. These are the numbers we use for counting stuff that's, well, whole. You can't really have half an apple or take a fraction of a step, at least not when we're counting this way. It's either a thing or it's not. Simple as that.
Okay, so that leads us to the big question. What are whole numbers really? Let's get a super clear definition, because this is the simple but super powerful foundation of, well, pretty much all of counting.
So here's the official, kind of mathy definition. Whole numbers are the set of non-negative integers. Whoa, okay, that sounds complicated, but it's not. All that means is they start at 0, and they just keep on going. 1, 2, 3, 4, and on and on and on, forever, to infinity. You know, sometimes the easiest way to figure out what something is to figure out what it's not. And let me tell you, whole numbers are pretty exclusive. Think of it like a club with some strict rules. Rule number 1. No negative numbers allowed. Sorry, -1, you're not on the list. Rule 2, no fractions. And Rule 3, no decimals. So 2.5, nope. They're just clean, complete whole units.
Okay, so where do these guys fit in the grand scheme of things? It helps to think of numbers as belonging to different families or sets. So let's take a look at the number family tree and see where our whole numbers have their branch. This chart is awesome because it just lays it all out so clearly. Check out the top row, natural numbers. Those are just your basic counting numbers, 1, 2, 3, the ones you learned first. Now look at whole numbers. They're almost identical, but they've got one extra super important family member, the number 0. Then as you move down the list to integers and rational numbers, the family just gets bigger and bigger. Integers welcome in all the negative numbers, and rational numbers throw a party for fractions and decimals. So you see, every whole number is an integer, but not every integer gets to be a whole number.
All right, so we know who they are, we know where they live. Now let's see how they play together. What happens when you add them, subtract them, multiply, and divide them? These are basically the rules of the game.
And this brings us to a really interesting question. If you take any 2 whole numbers, whatever they are, and you do some math with them, are you always going to get another whole number as your answer? Let's find out.
Okay, and this table perfectly explains a cool math idea called closure. It sounds fancy, but it just means staying in the club. So look, if you add 2 whole numbers, like 5 plus 3, you get 8. Yep, 8 is a whole number, so addition is closed. It's safe. Same thing for multiplication, but what happens if you subtract? Try 3 minus 5. You get -2. Uh-oh, that's not a whole number. We just got kicked out of the club. And division? 5 divided by 2 is 2.5. Again, not a whole number. So the big takeaway is that with subtraction and division, you can very easily end up outside the world of whole numbers. Now, these operations don't just happen randomly. They follow some really specific rules. And please, don't just think of these as boring old rules from a textbook. Honestly, they're more like the secret superpowers that make all of algebra actually work. First up, we've got the commutative property. This is the order doesn't matter superpower. For adding and multiplying, you can literally just swap the numbers around and you get the exact same answer. 5 plus 3 is the same thing as 3 plus 5. Super simple, right? But incredibly powerful. Then there's the associative property. This is the grouping doesn't matter superpower. So if you're adding or multiplying a whole string of numbers, it doesn't matter which pair you start with. You can group them however you want and the final answer is always going to be the same. And finally, the big one, the distributive property. I like to think of this one as the bridge that connects multiplication and addition. It's the rule that lets you distribute or hand out a number across a sum inside parentheses. And trust me, this one is a total game changer for solving algebra problems.
Okay, that's enough theory. Let's get our hands dirty and see how all this stuff actually works in the real world. We're going to go from some algebra to, even just a simple shopping trip.
All right, here we go. A classic algebra problem. Take a look. 2x plus 5 equals 13. Notice something? Every number you see there, the 2, the 5, the 13, they're all whole numbers. Our mission is to figure out what x is.
And we can knock this out in just 2 easy steps.
First, we want to get that x term by itself, right? So we subtract 5 from both sides of the equation. That leaves us with 2x equals 8. Easy. Now we just divide both sides by 2, and boom, x equals 4. And hey, look at that. Our answer, 4, is a nice, neat whole number. Perfect.
Okay, let's bring this out of the classroom and into the real world. Picture this, you're out shopping. You grab 3 shirts that are 15 bucks each and a pair of pants for 25 bucks. All whole numbers. So what's the grand total?
The math here is pretty straightforward. You just multiply those 3 shirts by $15, which gets you 45. Then you just add on the 25 for the pants. 45 plus 25 gives you 70. The total cost is $70. See? All whole numbers all the way through.
So it seems pretty simple, doesn't it? You start with whole numbers, you do some math, you end with whole numbers. But is it really always that simple? Well, our final section here has a little twist for you.
This really gets to the heart of it all. So let me ask you this. Does starting with whole numbers guarantee a whole number answer? I mean, look at this problem here. Every single number you see is a whole number. So the answer for x, it has to be a whole number too, right? Right?
Well, let's find out. First, we use that distributive property superpower we talked about. That gives us 2x plus 8 plus 3x plus 6 equals 22. Okay, now we combine this similar stuff. That gives us 5x plus 14 equals 22. To get x alone, we subtract 14 from both sides, and we're left with 5x equals 8. So the very last step is just to divide by 5.
And the answer is 1.6. Wait a minute. 1.6, that's a decimal. That is not a whole number. And this right here is probably the most important lesson of this whole explainer. So here it is. Even when your entire problem is built with nothing but whole numbers, the answer can end up living on a totally different branch of that number family tree. And that's the big idea. Whole numbers are absolutely the foundation. They're the bedrock of math, but they are not the whole story. They're just the beginning of a much, much bigger and more interesting world of numbers.